Okay, so today we're going to discuss closures of relations, which is section 8.4 in the sixth edition of the book. If you're using the eighth edition, that's going to be chapter 9. So it'll be 9.4. So we'll start out and we'll start out with an not such an interesting question, but imagine that we have connections between the various cities, and I put the Robert Crumb cartoon "Keep on Truckin'" here because the cities mentioned here are the same ones that are mentioned in the song, and probably at this point in the semester you're thinking, "Now, what a long, strange trip it's been," and indeed it has. So we let R be the relation containing the pair of cities A and B if there's a telephone line from city A to city B. And this is a much older example. How can we determine that there's a link between the call centers? Now, not all of these links are direct. For example, you can go from Boston to Denver, but you would have to go through Detroit in order to do that. And so we can't really use R to answer this. Furthermore, R is not transitive in this case. So in this section, we'll show how to find all the pairs of cities that do have a link. And we'll do this by constructing something known as the transitive closure of R in order to do that. And in this case, just looking at the graph, it's pretty obvious, what the connections are due to the simplicity of the graph, but we're going to talk about general procedures for doing this so we can extend it to more complicated examples. So let's talk about closures. Let R be a relation on a set A. R may or may not have a property P, and the properties we've discussed are symmetry, reflexivity, and transitivity, and anti-symmetry. A little bit less, but we've also discussed that. If there is a relation S with the property P containing R, such that S is a subset of every relation with property P containing R, then S is called the closure of R with respect to P. And this definition is kind of a mouthful. Let's see what it means by looking at the reflexive closure. So consider a relation R is equal to 1, 1, 1, 2, 2, 1, 3, 2 on A is 1, 2, 3. Well, this is not reflexive. We're missing 2, 2, and 3, 3. But if we added in 2, 2, and 3, 3, then we would actually make it reflexive. So by adding those two pairs in, the new relation, which includes those two pairs, is reflexive. It contains R, and it's contained by every reflexive relation containing R. So this is called the reflexive closure of R. So how do you construct that? Well, this one's pretty simple. We just basically take R and union it with the triangle, which is the delta, which is AA, where A is a member of A. Delta is also known as the diagonal relation. So what about the symmetric closure? Consider this relation R is 1, 1, 1, 2, 2, 2, 2, 3, 3, 1, 3, 2 on 1, 2, 3. It's not symmetric. What's missing? How can we make it symmetric and as small as possible? So we kind of determine what's missing. Well, we've got 1, 2, but we don't have 2, 1. So let's add that in. And we have 3, 1, but we don't have 1, 3. So let's add that in as well. And after we add those in, the new relation is symmetric. It contains R, and any symmetric relation that contains R needs to contain this new relation. So this is the symmetric closure of R. And the technique for constructing that is fairly simple. Basically, we union R with R inverse, where R inverse is BA, where AB is a member of R. So what about the symmetric closure of something more general? Say relation on the positive integers A and B, where A is greater than B. Well, what do we need to add in? We need to add in R inverse. So that would be BA, where A is greater than B. So it's basically the flipping them around. And so we end up with the set AB where A is not equal to B because the element can be both greater than itself and less than itself. And you can write this in a couple of other ways, such as BA, such that B is greater than A, but the answer here is pretty clear. Transitive closure. Okay, let's give this a shot. Hey, we got the symmetric and the reflexive ones pretty easy. Let's try the same technique by adding all pairs AC where AB and BC are already in the relation. Okay, let's give it a try with R is 1, 3, 1, 4, 2, 1, 3, 2 on A is 1, 2, 3, and 4. And we're gonna, try the same approach as we did with the last two. It's been a good approach so far. Let's see if it continues working. Okay, well, let's add 1, 2 because we have 1, 3 followed by 3, 2. That would indicate we need to add 1, 2 and we add that in. The other ones we need to add in are 2, 3, 2, 4, and 3, 1. So now S is this. So is this transitive? Well, no. So we have 3, 2 followed by 2, 4, but we don't have 3, 4. So this is sadly still not transitive. So what can be done? Well, we're going to look at how we construct the transitive closure, and that's kind of the main focus of this section. Little language arts joke here. Why don't you ever catch the ball? Sorry, coach, I'm intransitive and I can't take direct objects. And so transitive verbs are verbs that require direct objects, such as I bought a new laptop. So bought kind of requires a direct object. Intransitive verbs such as laugh do not require a direct object. For example, I laughed. So paths and directed graphs, and recall that we can represent relations as graphs. A path from A to B in the directed graph G is a sequence of edges x0 to x1, x1 to x2, x2 to x3, xn minus 1, xn. In the graph where n is greater than 0, x0 is A and xn is B, and that would take us from A to B through those intermediary nodes. The path is denoted by x0 to xn, and we'll have a length of n. We view the empty set of edges as a path from A to A. And a path of length n bigger than 1 begins and ends at the same vertex is called a circuit or a cycle. So let's take a look at an example graph. And here we have 5 different nodes. Which of these are paths? Which of them what are the lengths of those paths, and which ones are circuits? Well, if we take a look at the first one, we attempt to go from A to E, but there's no arrow going from A to E, so that's not a path. The next one, we can go from B to A, yes. We can go from A to C, yes. We can go from C to B, yep. We can go from B to A, yes. We can go from A to A. There's a loop from A back to itself. And then we can go to B. And look, we ended up where we started. So that one is, in fact, a cycle, and the length of that cycle is 6. DC, yeah, there's a path there. We don't end up where we started, so that's not a cycle. C to B to A, yes. And that one is of length 2, but it is not a cycle. Okay, E to B, yes. To A, yes. To B, yes. To A, yes. To B, yes. And back to E. And yeah, we end up back where we started. So that one is a cycle, and it is of length 6. And then we can go from A to B to E to D. We don't end up where we started, so it's not a cycle, but it is of length 3. And that's what we see here in the following table. I'll leave this up for a few seconds so you can verify that the table is correct, or you can pause the video and check that out. So there's a path from A to B in R if there's a sequence of elements with each one of those being part of the relation that take us from A to B. So let R be a relation on a set A. There's a path of length n where n is a positive integer from A to B if and only if AB is a member of R raised to the end. So finding the transitive closure is going to involve powers of relations. And remember, we went through that in a previous discussion. And we're going to determine which pairs are connected by the graph. So what we can do is we can do the connectivity relation, which is R star. And it consists of the pairs A, B, such that there's a path of at least length 1 from A to B in R. And that goes up to infinity, so the path could be as long as we need it to be. So, real world example, and I don't know if we've talked about the 6 degrees of Kevin Bacon, but nearly everyone in Hollywood is connected to Kevin Bacon by a relation of at least 6 degrees. So, um, basically, you can link actors and actresses to Kevin Bacon with fewer than 6 steps, and that's called the 6 degrees of Kevin Bacon. So he's kind of at the center of that Hollywood graph. We get more into that in the social networks class. So what is R to the n where n is an integer greater than 1? And here AB means that A has met B. So, if we look at, Rn, it means that there's people such that x1 has met x2 and x2 has met x3 all the way up to xn minus 1 who has met B. So that connects them. R star contains AB if there's a sequence of people starting with A and ending with B, such that each person in the sequence has met the next person in the sequence. So find a path between you and Kevin Bacon. I meant to replace Fidel Castro with Ozzy Osbourne because Ozzy Osbourne is at the center of the music graph, and the Dalai Lama. And so you can kind of see that, you can connect people through very small degrees of connection. I think it's 6 degrees of separation is the general theory behind how closely related we all are. So another example would be find the set of all subway stops in Tokyo that contain A, B if it's possible to travel from A to B without changing trains. What is Rn? What is R star? Well, Rn contains A, B if it's possible to travel from A to B by making n-1 changes of train. R star consists of A, B, where you can go from A to B by making as many changes as necessary. And we'll take a look at what the Tokyo Metro looks like. And wow, if you like complicated graphs, the Tokyo Metro is definitely your thing. So here you can see Tokyo Station. It's M17, I believe. And can we get from Tokyo Station to Shinjuku? And yeah, we can do that without changing lines, and you can kind of trace through that. R2 would contain Tokyo and Shimbashi, since you have to change once at Shinjuku to get to Shimbashi. And then you could see, what R3 would contain. In some of these more far-flung stations, you're definitely going to have to make a change of train. A graph or a map of the United States. It R contains the set of all states A, B if states A and B have a common border. What is Rn and what is R star? So Rn consists of A and B, where it's possible to go from A to B crossing exactly in borders. So, if it were, possible to go across 2 borders, say you wanted to go from California to New Mexico, you could go across the Arizona border and then from Arizona into New Mexico. And that would be part of R2. R star means it's possible to get from A to B crossing as many state borders as necessary. And as always, Hawaii and Alaska get excluded from this conversation, as does Puerto Rico. Puerto Rico is not a state, but they're part of the family. So, and of course you get these crazy maps in the mainland where they don't know where to put Hawaii, Alaska, and Puerto Rico. I think Puerto Rico is probably correctly positioned. Alaska is definitely not, and looks like Hawaii has become part of Mexico now. So, hola. So the transitive closure of the relation R equals the connectivity relation R star. Now, we said that R star was infinite. It seems like a lot of work. We but we don't need to examine arbitrarily long paths to determine whether there's a graph containing two vertices in the graph. In fact, it's sufficient to examine paths containing no more than n edges, where n is the number of elements in the set. So we can limit that down a bit. So we can formalize that with lemma 1. Let A be a set with n elements and let R be a relation on A. If there's a path of length at least 1 in R from A to B, then there's such a path with length not exceeding n. Moreover, when A is not equal to B, if there's a path of length at least 1 in R from A to B, then there's such a path with length not exceeding n minus 1. And recall that we can make mostly interchangeable statements about things. So let M sub R be a 0, 1 matrix. So, we can talk about graphs and we can talk about matrices, and we showed, how they can both represent relations. Then the transitive closure MR star is basically MR union or MR2 or MR3 or MR up to the n, where n is the number of elements. So find the 0, 1 matrix of the transitive closure of the relation R, where M sub R is equal to this matrix. Well, we can get M R squared, MR cubed, and union or those together. And basically we have to do a lot of matrix multiplication, but we can get MR2. The good news is that MR3 is equal to MR2. And unioning those two basically gives us MR star, which is the same as MR2 and MR3. And so we only have to go from 1 to 3. It's not horrible. And in fact, there is an algorithm to do this. Start with A is equal to M sub R, B is equal to A, and then do the multiplication, and then do the OR between B and A, and B is the 0, 1 matrix for R star at the end of this algorithm. The bad news here is this algorithm is O of n to the fourth in terms of bit operation. So can we make it more efficient? And there is a more efficient way of doing that, and it's an algorithm known as Warshall's algorithm. And in fact, this one turns out to be O of n cubed, which is helpful for us getting things done much, well, not incredibly quick, but quicker than O of n to the fourth. And that's because Warshall's algorithm only uses interior vertices. And note that the first and last vertices visited are not interior vertices unless you visit them somewhere else on the path. So based on the construction of a sequence of 0, 1 matrices, W0 through Wn, where W0 is MR and Wk is equal to W sub ij raised to the k, where it's equal to 1 if there's a path from Vi to Vj such that all interior vertices are in the set V1, V2 to Vk. Otherwise, it's 0, and that will work because W sub n is equal to MR star. So let's see an example of this. This is kind of a bit of a difficult conceptual thing to wrap our head around. Here's our relation represented as a graph. We'll let A, B, C, and D be the listing of the elements of the set. We'll find W0 through W4, and W4 is going to be our transitive closure. Okay. So we start with V1 is equal to A, V2 is B, V3 is C, and V4 is D. W0 is the matrix of the relation. We can go from A to D. We can go from B to A. We can go from B to C. We can go from C to A. We can go from C to D. And we can go from D to C. Okay. It's fairly straightforward. W1 has a 1 at its ij entry if there's a path from Vi to Vj such that V1 is equal to A as an interior vertex. All paths of length 1 can still be used. Now, here we can see there's a path from B through A, and then we can get to D. So we can get from B to D by going through A. So we add that one in, and that one's circled. Now W2 has its ij entry if there's a path from Vi to Vj that has only V1 is equal to A and V2 is equal to B as its interior vertices. All paths of length 1 and 2 can still be used. B has nothing going for it. In fact, it's only a source state. There's nothing that's going into B. So W2 is equal to W1. But we're not done. W3 has one as ij entry if there's a path from Vi to Vj such that it has only V1 is equal to A, V2 is equal to B, and V3 is equal to C as its interior vertices. Now, all the paths of length 2 from the previous one can be used, but notice we can go from D to C to get to A. So we can add D to C to A, which is the one in the bottom left, and D to C back to D. And we can add that one in on the bottom right. Now, last step, W4, we can add D as an interior vertex, and then we can go from A through D to C. So we can add that one in. We can go from A to D to C to A, and so we can add A to A in. And then we can go from C to D to C, and so we can add the C to C one in. And so all three of these are circled. This is our transitive closure. And here is Warshall's algorithm. And basically, we're unioning those individual matrices at each individual step. This algorithm is O of n cubed with a total number of bit operations equal to 2 times n cubed. And that's the end of the presentation. Thank you so much for watching.